Okay, today we're doing exponential growth and decay. We are going to be looking at graphs. That's why the graphing calculator is up. All right, this is the exponent chapter. So what we have in front of us is a nice little exponent. We have our base, we have our exponent. Now, remember, this base cannot be a 1 or a 0. In other words, we can't have y equals 0 to the x. If I came over here and I graphed that very quickly, I get nothing. That's right, because if we look at the table, 0 to any positive power is 0. And we can't do 0 to negative powers because remember, anything raised to a negative power would tell us to flip this, thus creating 1 over 0, squaring it, and we can't have 0 in the denominator. I think by now you can figure out why we can't have 1 as a base. Because I don't get any growth or decay. I get a straight line. Growth means to get bigger, decay means to get smaller. If I look at my table, and that's because anything raised, 1 raised to any power is 1. Now, you've already done exponential decay. You did it in chemistry. In chemistry, it was called half-life. So you started off with a substance, you were giving its lifespan, and you would say every, 50 years, half was left. And then another 50 years, and half of that is left. And then half. And then half. So what Shu was telling you is that you never really lose the stuff. You always have half of what was it left. So it never goes down to 0, because I can always have half of something. All right, so let's look at a couple of graphs here. Let's look at the first one. This is something they'd ask you to graph in your homework tonight. You'd graph it. Aw, look how pretty that is. And then you know you can go right to your table. And if you were to graph it, those are the pretty points. This is an example of growth. This is exponential growth. And since the base is 2, this is talking about doubling. So pretty much if this were looking at a year, every year something is doubling, right? When you begin at 0, you have 1 of something. Now the next year you have 2, and then the year after that you have 4, and then the year after that you have 8. And basically this is how humans grow. You start off as 1 cell, and then you double, and voila. All right, so what was this? I'm going to come over here to y equals. I'm going to make this just a little bigger so you can see this. And I'm going to write 2 to the parentheses negative x. The next thing I'm going to do is watch my key. My cursor is moving over to the left, all the way to my line. See how the line is blinking? Now I'm going to come down here and press enter. By doing that, I've created a darker line. So now when I go to graph this, I get to see both pictures. One's darker than the other so I can tell them apart. Now I know this looks like it goes below 0, but it really doesn't. See, as I get larger, the numbers get closer and closer to 0 as y values, but it never really reaches 0. And this, boys and girls, is a half-life. This is decay. And it makes sense because the graph is going down. Notice also that I negated the x value. Here it was positive, and in here it was negative. So another way you can look at this if you negate the x value, you end up flipping over the y-axis. And the last thing we have to look at are our asymptotes. What line do we get very, very close to, but these graphs never touch? Both of them get very, very close to the asymptote y equals 0. Remember, that's the game you played with your little brother or sister. You can't touch, I'm not touching you, I'm not touching you. And you try and get as close and close and close and close. You played the asymptote game. Real quick at these three graphs. The first one's up there, y equals 2 to the x. The next one is a little different. I want the negative out front. And then I want, in parentheses, 2 to the x. And let's look at those. Let's graph those. There's my original. And here's my next one. Hey, this one's a little funky. Oh, but that's right, you get it now. See here, I negated the y value. So it flipped over the x-axis. And now I'm going to come over here and I'm going to enter in this third graph. Parentheses, -2. Now I'm going to end the parentheses and I'm going to raise that to the x. Hey, it didn't show up. Alright, I'm going to come over here and I'm going to turn off these other two. Maybe it was on top of them. Whoops. Turn that off. Graph. Let me look at my table, see what's going on here. Oh, yeah. Look at the y values. Positive, negative, positive, negative, positive, negative. Oh, no. If I come back here, what I have just shown you is an example of a divergent sequence. If I tried to graph this, let me go back here, and I tried to graph this, look what would happen. When I'm at 0, I'm at 1. When I'm at 1, I'm at -2. When I'm at 2, I'm at +4. When I'm at 3, I'm at -8. What I'm having here is positive, negative, positive, negative, positive, negative. You can see why it's called divergent now? It's going in two different directions. And the calculator can't handle it. And these were just the whole numbers I looked at. This happens with even all the fractions and decimals and irrational numbers in between. So the calculator just can't graph it. So here we have an issue when the base is negative. So we had an issue when the base was 0, when the base was 1, and now when the base is negative. Hold on to that thought for the summary. Okay, take a guess. Do we think this is a exponential growth or an exponential decay? Well, one way to find out. Pop it into your calculator. 1 divided by 3 to the x and graph. It's exponential decay because my base here is in between 1 and 0. We will always get decay. That's half-life. Right? If you did this in Shoes class, this is the equation for half-life. Last example. E. What the heck is E? No, it doesn't mean double variables. Right now, you know that pi is 3.14. Well, in upper level math, we have E, which is 2.71. And you can find E right here on your calculator above the division sign. E was founded, actually wasn't founded by Euler, but he did the most work with it. And that is pronounced Euler, not Euler. He found it, and actually people always say E, Euler's number. He did the most work with it, although it was around. This is more important as a number than pi. E is found in all naturally found in all carbon life forms. That's why in AP Chemistry you often use this natural logarithm key down here. And what's more, it's in financial. This little number right here runs the economy of the world. It's used in all banks. It's used in all financial calculations. We don't really do much with E in Algebra 2. You do a lot more with it in pre-calc and a heck of a lot of it with it in calculus. We just kind of introduce it to you and say, it's here. We'll do a little work with it more in Chapter 8. All right, so here's the summary of the lesson. When we're doing exponential graphs, the base must never be a 0, a 1, or a negative number. We gave you examples of why those don't work. If the base is greater than 1, then we have exponential growth. We gave you y equals 2 to the x, and then we gave you y equals e to the x, because e is 2.71. That's definitely greater than 1, so we're going to have double and a little more growth every single time. Now, I want to clarify this. If b is less than 1, knowing the fact that it can't be a negative number. So you could also write it this way. If the base is a number between 0 and 1, then we have exponential decay. And we showed this when we did 1/3 to the x. We got decay. Okay, done.